Hello students, this video is my first attempt on making a math video, so let's start with something simple. Let's prove the theorem that says that the shortest distance in a sphere is an arc of great circle. So let me show you here the slides. So this is the assertion that we are trying to prove. You have a point A on the surface of a sphere, and you want to travel to the point B through the shortest distance while remaining on the surface of the sphere. We're going to prove that this is an arc of great circle. So a great circle is a circle that pertains to a plane that contains the center of the sphere. What you're seeing here is a sphere being bisected. A plane that bisects the sphere has to pass by the center. Where this plane intersects the sphere, you have a great circle. An example would be the equator of the Earth. It is a great circle. A sphere can be sectioned by small circles or great circles. So the great circle is the one that passes by the center. Small circles are the ones that do not pass by the center. You have parallels and meridians on the Earth. Meridians are great circles. They all intersect at the poles and bisect the sphere. Parallels are not. Parallels are lines of constant latitude, and they are small circles. Meridians are lines of constant longitude. So let's see how we can prove that the shortest path is indeed an arc of great circle on the sphere. Here to the board, it's something that I'm going to be doing frequently in this course, passing back and forth between the slides and the board. So let's start with the proof. So we want to prove that this is an arc of great circle. So to prove this theorem, let's use the definition of Cartesian coordinates. Conversion between Cartesian and spherical coordinates. X is the radius, r, times sine of theta cosine of phi. Y is r sine theta sine of phi. And z is r times cosine theta, where theta is the meridional angle. Where theta is the meridional angle. And phi is the azimuthal angle. On Earth, once the pole is defined, phi would be the longitude and theta would be the co-latitude. Not the latitude, but the co-latitude. We can define also the line element. The line element is going to be the S is equal to VR r hat plus r d theta theta hat plus r sine theta d phi phi hat. We can square this to be then dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. Now we want to know the distance. The distance is the integral of this elemental, the path elemental, going from A to B. So now we make use of the fact that we are on the surface of the sphere. So there is no movement in radius. You cannot go inside or outside the surface of the sphere. Therefore, dr is equal to 0. There is no variation in radius. And also, we are free to choose whatever radius we want for the sphere. So we choose the radius of the sphere to be 1. It's a sphere of unit radius. With this substitutions, the path element, the S, becomes d theta squared plus sine theta squared d phi squared, and of course the square root of this. So substituting it back on the length, you have that the length is going to be the integral from a to b of the square root of d theta squared plus sine theta squared d phi squared. Now we isolate the d theta, we take it out of the square root, and this becomes then d theta times the square root of 1 plus sine squared theta d phi squared d theta squared. Immediately in here, you can see that this integral, that this integrand is going to be minimized when you have d phi equal to 0. So already you see here, L is minimized when d phi is equal to 0. What does that mean? So what is the geometrical interpretation of d phi being equal to 0? You're passing from the point A to the point B, and the distance that you have to travel to pass from AB is minimized when d phi is equal to 0. That means when you do not change your longitude. That means that you're walking along a meridian. The meridian was an arc of great circle. Remember that we did not define here where the pole is. Once you define where the pole is, this is an arc along a meridian. So that proves that L is minimized, the path is minimized as you're walking through a great circle. So the theorem here is proved QED. Thanks for watching, folks. Till next time.